In this video we are going to learn how to calculate the Jacobian matrix for spherical coordinates. The Jacobian matrix, here denoted as JF for Jacobian of the function f, is defined in such a way that it contains all possible partial derivatives of a vector-valued function. What that means is the following. If our function f is a vector, that vector is obviously going to have multiple components. The higher the dimension, the more components. For the first row of the Jacobian matrix, we're going to take the first component of the vector and differentiate it with respect to every variable. So if the components of our function are f1 up to fn, and the variables of our function are x1 up to xn, then we're going to start with the derivative of the first component with respect to the first variable. We're then going to move on with the derivative of the first component with respect to the second variable, etc., until we run out of variables. In the second row, we're going to do the same for the second component, etc., blah, 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 until we run out of components, which means that the number of components of our vector determines the height of the matrix, and the number of variables those components contain determine the width of the matrix. In this particular case, we are looking at the transformation from Cartesian coordinates to spherical coordinates, and that transformation looks like this. Every Cartesian x turns into r sine theta cosine phi, every Cartesian y turns into r sine theta sine phi, and every Cartesian z turns into r cosine theta. Our transformation has three rows, so this is going to be f1, this is going to be f2, this is going to be f3, and we also have three variables, namely r, theta, and phi. That means our Jacobian is going to be a 3×3 matrix, and that matrix is going to look like this. In the first row we have all partial derivatives of f1, in the second row all partial derivatives of f2, and in the third row all partial derivatives of f3. For the very first entry, in the top left corner, we have to differentiate f1, so this component here, with respect to r. That means the factor of r is going to fall away, and we are left with sine theta cosine phi. Next, we have to differentiate the first component with respect to theta, so we can treat those two factors here as constants. The derivative of sine theta is cosine theta, so r cosine theta cosine phi. And lastly, for the first component, we're going to have to differentiate it with respect to phi. Now these two are treated as constants, and the derivative of cosine phi is minus sine phi, so we are left with minus r sine theta sine phi. For the second row, we now need to take a look at the second component. Differentiating that one with respect to r leaves us with sine theta sine phi. Differentiating it with respect to theta means that these two are treated as constants now, and the derivative of sine theta is cosine theta. So we get r cosine theta sine phi, and differentiating the second component with respect to phi gives us r sine theta cosine phi. For the last row, we're going to have to take a look at the third component, which is simply r cosine theta. Differentiating it with respect to r gives us cosine theta. Doing so with respect to theta gives us minus r sine theta. And differentiating the third component with respect to phi simply gives us 0, because the third component doesn't even contain phi. So this is just a constant, and the derivative of a constant is 0. So this is our Jacobian and spherical coordinates, and in the next video we're going to take a look at how we're actually going to use this to transform a volume integral from Cartesian coordinates to spherical coordinates. I'm going to link that in the description down below as soon as it's uploaded, so stay tuned. I really hope you found this video helpful. If yes, consider sharing it with a fellow student who might also benefit from it, or subscribing to the channel. Thank you so much for watching, and see you in the next one.